So another example of how we can use the RL tool in MATLAB is for our second example about integral control that we talked about in lecture. In this example, the plant was s plus 2 over s squared plus s plus 3, and the open loop step response looked like this. And what we can see is that the settling value, the final value, is somewhere between 0.6 and 0.8, when we'd like to ideally be tracking the number 1 because our step input was a unit step input. So this is actually a pretty poor tracking in that there's this large steady state error. So what we wanted to do was test a controller, an integral controller of the form k over s. Now remember when we talked about integral control in our PID sections, integral control helps with that steady state error and can eliminate steady state error such that we get perfect tracking in the long run. So what we attempted to do was to use this type of control and figure out what our closed loop step response would look like. So what we did was to draw the root locus for this type of controller. So the root locus actually looks like what's shown here, and we found out that actually at some point, if our k is increased too much, we can send our closed loop poles into the right half plane, which is what you're seeing here. And so in class we determined that that value is 3. And what you can see is now the closed loop poles are right on the border. They're right on the imaginary axis. And if we increase k anymore, they'll traverse into the right half plane, sending our entire closed loop system unstable. So this was another example about how we can start with a perfectly stable system and send it unstable using feedback control. So we got to be careful with integral control. What I want to show you now is sort of the RL tool application. So we can use RL tool on this system, and we can actually see very quickly what our root locus looks like and what our closed loop poles are doing as we increase k. So in the open loop, we essentially have k is 0. So our loop gain is basically 0. What we're seeing is how the closed loop poles traverse the root locus as we increase k. And again, right as we hit about k is equal to 3, 2.93 here, we're just about to cross into that unstable region. So now k is 3.22. We've sent our whole system unstable. So this is a really cool kind of visualization of how the root locus actually works as you increase and gain k. So what we can do again is go to analysis plots and look at a closed loop step response. And we can actually see what happens. So we've got our closed loop poles kind of moving along the root locus as we increase and gain k. We're still stable. And you'll notice that as long as all of our closed loop poles are in the left half plane, we're stable, and that integral control is actually eliminating that steady state error. So we are actually tracking at 1 using the integral control, which is great. Just keep in mind that if we increase it too much, what you're going to see is that the step response will actually go unstable. But in any case, this is a kind of a cool visualization and an application of the RL tool for the second example that we did in class about integral control.